Okay, I've heard from a couple of people, they were asking me about relative extremes. I don't call them relative extrema. I mean, you can call them, that's fine. That's what most books call them. But your relative maxes and your relative mins are also referred to as local maxes and local mins, and they will interchange those two words on an AP test just from one problem to the next. Mainly because probably different people are writing different questions. But if it's a max, then you don't say anything in front of it unless you want to say absolute or global. But you could say absolute, which is the highest Y value, absolute max, or global max, which is the highest Y value, or you can just say max. But if you're referring to a local or a relative, you have to say local or relative, all right, with max or min. And when you're referring to relatives or local maxes and mins, it has to be the highest point in that area higher than the points on the left or the points on the right. And I was speaking with Akram earlier, and there was a problem in your homework which did something like this. And the book would refer to that as a local max. And if it was the highest point, it would be a max for sure. But calculus tends to have a weird definition that's a little different, and you're going to see that today and tomorrow, or today and Monday. Calculus is a little bit different than pre-cal. Pre-cal defines in terms of its definition. And I've talked to professors about, like guys that were doctorates, and I'm like, hey, reconcile this with me. And they're like, yeah. And they tend to just kind of avoid the issue, which is bizarre to me. But the calculus definition says that it is considered a relative max if the Y values to the left and to the right of it are smaller, which makes sense, right? It's the biggest one in the region. But calculus is all about the way the slopes and the derivatives work. So you're going to see that definition a little bit different. And I'm like, well, how can you just be bouncing from one definition to the other? Like, well, and you'll see this in calculus, and I have searched, I've probably taken easily 20 to 25 AP tests. Never once has that popped up. They always deal with continuous functions when they're talking about relative maxes and mins. So you never see that issue. So what you always see is maybe something like, slopes are positive. You're going to see this definition today. Slopes are positive from one side, negative from the other, hitting zero. Relative max. Slopes are negative from one side, positive from the other, maybe undefined. Relative min. They define it like that, but you're never going to see situations like this or like this. In pre-cal, your definition would hold, it would be fine. It doesn't really assume that things must be continuous there. But in calculus, they try to avoid the issue. So there are a couple of problems that were in your book like that. I'm going to avoid it as well. I'm not going to quibble about the differences in the definition. And I think you'll see that over the course of the next 2 days. When we start defining, how do you define a max or a min? You'll go, oh yeah, I kind of see what you're talking about. But anyway, if you ran into a problem or two like that in the book, remember this book is not really, they call it an AP edition, which is a joke. He just tagged that on there to suck us calculus teachers into buying it. An AP edition. And when we first bought this book, it was I had taught calculus 1 year, which stunk for me because I had to do all of my homework problems and figure them all out in one book, and then I tossed the book and I had to start over. But I really didn't know what I needed at that point. That early in the game, I really didn't know what a great AP textbook would be. This is not one. And I don't think there is one. I think a great AP textbook would be something that a good math AP teacher would write, and it would be a lot more user-friendly, and it'd have a lot more AP-style problems, but it's just not there. So my little books that I give you have a lot more of those AP-style problems in there. But anyway, that was something I want to point out. And also, relative maxes, they can't occur at an endpoint. Again, it has to come in from both sides, okay? So you can have a max at an endpoint. They can go up there, be a max, right? If there's a point there, right? Not if there's an open circle there. But if there's a point there, you can have a max there. But a relative has to have something going on either side, all right? And this is something that I actually took in a graduate level class. It was called Elements of Real Analysis. Worst class I've ever taken in my life. And if you remember Colin Clifton, which you might, y'all were freshmen, he was a senior, his little brother's a 10th grader this year. But he was a really, really bright guy, national merit guy, 36 ACT or 35. But he has made 1B in Auburn in the actuarial science program, and it was in that class. It's brutal. But I remember taking it, and we dealt with something called bound theory. And like, say I had a problem like this, and it stopped there. And the question was, and let's just say that is at 5, and that is at 2. Okay, so you got this graph. And they said, what's the min? And it was very easy to see that the min was 2. And then it said, what's the max? Well, you can't say it's at 5 because there's nothing at 5. So what would you say? It actually doesn't exist. But the problem, people are like, what do you mean? But can't you get really infinitely close? I mean, what about 4.999? I'm like, well, then what about 4.9999? And people are like, well, what about 4.9999999? Then you could always say, what about 4.999999999? And then if you said, what about 4.9 repeating? Well, what's 4.9 repeating? 5. So you can't say.
The last time it did.
So 4.9. You're probably right. You'd probably say 9.9. So 4.9 repeating would be 5, and it's clearly not 5. And there's a whole branch of math called bound theory, like getting as close as you can, but you can't really get there, that explains that. And I remember having to prove that in this class. It was just horrendous. I remember studying somewhere in the neighborhood of 70 hours for a final. And I remember sitting right there in the class. We walked in there. It was me and this little squad of mine that we studied together. And we would study 8-9 hours a class period just for a homework assignment. And then we turned it in and we'd get 70s. Except this dude named George. George was a genius.
We don't have George in this class this year to say it.
That's true.
He's in the other one.
But he's in the, yeah, he'll be back.
Maybe we'll have him on
Wednesdays.
But anyway, George in this class, and some of you have heard this story, but he was a genius, but he didn't know how to communicate. I'd be like, George, I see what you're doing. I understand what you're doing. How did you know to do that? Dude, I just know. I was like, that's not helping. But anyway, this class was horrible, and I think they handed the test. I remember they handed the final, and I had a C. I had straight A's in grad school. I'd never made a B, and I had a C going into the final. I'm like, oh my gosh. And I'm starting to think, okay, I've already accepted a C. And I'm thinking, but the finals are 60%. I said, if I bomb this final, I can make a D in this class, and then I can't graduate. You can't graduate in a master's in your major with anything lower than a C. And I'm like starting to worry, because if I don't graduate, I don't teach here in the fall. And everything changes. And I remember him handing me the test, and there were 11 questions on it. And I looked down, and I'm scanning it as he's handing them to other people. I'm like, okay, I know how to do 5 of these. I can kind of, whatever my way through a 6th. And I'm doing the math in my head, 6 out of 11. Oh my God, I'm dead. And right about that time he goes, all right, class, this test is way too long to get finished in this time period. So tell you what, just pick your favorite 6 and I'll grade, no, what do you say? Pick your favorite 6 and I'll just grade those. Or pick 6 and I'll grade those 5, or I don't remember what he said. But I remember thinking, actually I did that. I raised my hands in victory. Because I knew I was going to kill this thing. And I did. I had a 95 on it. My average jumped from a C to a B, and then everybody else, except the couple people in my group, got hammered. And I even beat George on that one. But everybody got hammered. And the grades were so bad he scaled. So I ended up getting an A from the bowels of defeat to an A. It was pretty awesome. But anyway, we talked about bound theory in there and a bunch of other stuff that hopefully you won't ever have to deal with unless you're a math major or an actuarial major. But make sure you understand these definitions. I know that some of this stuff looks really wordy, but if you start staring at it, it'll start making sense. Like, a lot of people see this and they're like, what the heck does that mean? But what does f of anything mean? The y value. So it's saying, hey, the y value at this c is bigger than the y value for any other x. That makes it a global max if you have the biggest y value. The y value is smaller than or equal to all the other y values in an interval. That makes that a global min. So these definitions will start to make more sense if you force yourself through this language. And it's important that you do that as we're moving through this material. And ask questions like, different people pop in here now, little bitty things. Those little bitty things are going to be a big deal come this test and come the AP test. So if you jump down to, we've done mean value theorem and all this. We are on page 117. Okay, so increasing, decreasing, and constant, and the first derivative test. Huge Jeez, this is 117?
113.
What?
For us.
Your pages are off.
Really?
Yeah.
Yeah, in the video it's not fixed too.
Weird. Because this is my current thing. Maybe.
Where did he?
Oh well, whatever. Said 113?
Yes.
Okay, so increasing and decreasing constant. This is going to make perfectly good sense, I think. But if you just thought, oh, I feel good about it, then you're going to miss stuff. I'm going to ask you questions like, if the first derivative is greater than 0, then what does that mean about the function? It's going to be fill in the blank. Now, as I go through these, you're going to go, oh, that makes sense. And if it doesn't, ask me, okay? So, a couple things I want to talk about. If I have time, I'll come back and talk about these, but these are just some practice problems about finding extreme maxes and mins. And hopefully we already know how to do that, right? To find a max or a min, where do I look? Critical numbers or endpoints, and I find critical numbers by setting the derivative equal to, taking the derivative and finding out where it's either 0 or DNE, or undefined. And you can see on a square root function, that square root's going to end up where? In the denominator, right? When you take the derivative. So there are going to be places perhaps where it's DNE, and there are going to be places where it's 0. And you find those, and then any of those values that you get, remember that they're not always critical numbers, because sometimes they're not even in the interval, right? Depends on what interval I give you. So it says, why isn't negative 1/4? If you do this problem, you'll see one of the answers you get is negative 1/4, and you're like, oh, well, it's not even in that interval, right? Wait. Oh, yeah, it is. Why isn't it negative 1/4? Because on negative 1, I guess I probably ought to do the problem. I guess I'd have to go back and look at it. And then from this function, find the value of C that verifies the mean value theorem. Do you remember what mean value theorem is asking you to do? We did this yesterday, you weren't here, but mean value theorem says basically what? One of the conditions is the function has to be continuous on a closed interval, differentiable on an open interval, but what does the mean value theorem says? It says that the slope from beginning to end, which is the average rate of change, that's the right side of the equation. That slope from beginning to end will occur at least one time somewhere else in the graph. And that means what? The slope occurring somewhere else would be the instantaneous rate of change, the f prime. So the derivative of the function at some value will be the same as the average rate of change, which is the slope from beginning to end. And that's guaranteed if it's continuous on a closed and differentiable on the open. And then Rolle's theorem just adds to that. It says, hey, if it's continuous on a closed and differentiable on an open, Rolle's theorem says, oh, if your y values at the beginning and the end are the same, then what? The derivative somewhere is guaranteed to be 0, because essentially the average rate of change would be 0, right? If you start and finish in the same spot. Are y'all with me on that? Now you have to know those things. I'm going to test you on those things, and I'm going to keep reminding you about it, and we're going to keep reviewing and stuff like that. But now I want to get to some increasing, decreasing, and probably the most used test on this AP test that you'll see is the first derivative test. And it's not rocket science, okay? But you do have to understand the language, and sometimes the language looks like this. So let's just walk through it. It says, if a function's differentiable on an open interval. So by telling you it's differentiable, you also know what? It's continuous, okay? So now we know we got a nice smooth function with no breaks, no holes, no asymptotes, no funny cusps, no going vertical, none of that junk, right? Okay, so if it's differentiable on an open, which means who cares about the endpoints? What does this mean? The slope of the derivative. So if the slope of the curve. If the derivative or the slope of this function is positive, that's a positive slope, right? Then isn't the function increasing?
Yes.
So, that's the rule for testing increasing. So, if I took a derivative and I just plugged a number in and I got positive 7, then you go, oh, that must be increasing on that region. If I got positive 2, oh, it must be increasing on that region. If I got positive 1, oh, it must be increasing on that region. I know that. Okay, and vice versa. If I knew, well, I'll get to that later. Okay. Second thing, if the derivative of a function at a particular value, or on a particular interval, is smaller than 0, that means slopes are negative, then it must be decreasing. Don't say it anymore. Because when you say it, I'll say it all the time and I'll try to correct myself. But it is what you're thinking f, right? You're thinking, oh, it, the function. But I'm going to be talking about the function, the first derivative, and the second derivative all mixed together. It is not going to work for you. So don't use the word it. Just banish it from your language on this test. When you're speaking, if you say, oh, it's increasing, I'm going to go, what's increasing? Is the function increasing? Is the first derivative increasing? Is the second derivative increasing? We're going to have to differentiate between all those things. Okay? Because think about it, when you take a derivative, don't you get this new formula? Couldn't you graph that function? It's probably going to look different, isn't it? Because it's a totally different function. So there's actually a derivative graph. We haven't been doing any of that yet. That's what we're about to start. But you got to understand, we can't use it. We have to be really clear about what we're talking about. All right, so if the derivative of the f, or the slopes, are negative, then the function f must be decreasing on whatever that interval it was named. Okay, and if the derivative is 0, what does that mean? If the derivative is 0, then it either hit a high spot, right, or maybe a low spot, or it is possible, I think I have one here. Yeah, it is possible you could hit a 0 there, but it's also possible you could hit a 0 there. Kind of seeing that? That for one instant it went horizontal, not it. For one instant, the derivative of that f prime went 0 right there. Okay? Now, so when I find the derivative of f equals 0, we call those critical numbers. And not all critical numbers end up being maxes and mins, or relative maxes and mins, do they? Sometimes you get an undefined like this. This is a place where this derivative is undefined because it looks like a corner or a cusp, right? But clearly was a relative min, low spot. Right here, the slope was 0, but clearly not a relative max or min, right? Here, slope of f was 0, clearly a relative max, and maybe a max if I knew more about the graph. Here, relative min. Are you following me? So anyway, that's all these things we're saying about rules for increasing, decreasing, and constant. And rarely will you ever see this. I don't even have a memory of seeing something like that on an AP test. But right here, clearly on that whole interval, the slope would be 0, wouldn't it? All right? All right, so that's what they're talking about when they say constant. All right, so if it's 0 on an interval, it's constant, but I doubt you're even going to see that. Usually it goes 0 at one point. So it's not a constant spot right there, but it's occasionally, I guess, that could happen. Okay, now, let's jump down here a little bit. So hopefully you know that we are increasing from like negative infinity to a, right? And I'm not saying negative infinity because it's going down. I'm saying negative infinity because what? Left. I'm coming in from the left, right? So I'm coming in from the left to a, increasing. From a to b, the function is decreasing. And then from A to B, decreasing, and then from B to infinity, and again, I'm going to infinity because I'm going to the right, not up. Everybody with me on this? I'm going to lock in, okay? And that's another increasing. Right here, from negative infinity to A, decreasing, right? From A to B, constant. From B to infinity, increasing. And notice I don't have any brackets, do I? Why don't I say from negative infinity to a with a bracket for that increasing? Because there's a point there. At the point, it's actually not even constant, because remember, constant has to be an interval.
Or the derivative is 0.
The derivative is 0, but right here, it's neither positive nor negative, right? That's where it's 0. And to be increasing, it would have to be positive. So because it's neither positive nor 0, and if you just go ahead and lock that in your brain, when I'm writing out intervals of increasing and decreasing and constant, I am never going to use a bracket. You're never going to use it. I can actually come up with I could actually write one, like right here. I could say, well, what about from C to D? Yes, from D to C, I could put a bracket on that, because yes, even at those points, but guess what? We don't ever do that. I'm not interested in D to C. I would be interested in the whole increasing region. So in the work that you do, just remember parentheses, is going to be great for you on all of your intervals where you are increasing and decreasing and constant if you should ever see that. Now, this puts it all together. This is the biggest deal in APCalc, probably most commonly used situation or rule that you'll have. It's usually pretty obvious when you make sense of it, but you need to be able to know this when you see it worded like this. And then later you're going to have to be able to know this rule when you look at graphs and all kinds of things. So what this says is, this is called the first derivative test. There's also going to be a second derivative test for finding relative maxes and mins. So you've got two tests for finding relative maxes and mins. Okay? First derivative test. If C, let C be a critical number. So bottom line, how do you find critical numbers again? Set the derivative equal to 0 or d/e and figure out what those x values were. So once you have those x values that may or may not be maxes or relative maxes, we don't know. They're just possible relative maxes and mins. And by the way, this is not extremes. These are just relative maxes and mins. They may turn out to be maxes and mins. But we don't know that. We would have to check those and also check the endpoints, right? We already know how to do that. This is for relative maxes and mins. So get this down. Make sure you understand this. If it's a critical number, so you've already found out and you know that the slope is 0 or d/e there. So if it's a critical number and the derivative changes from negative to positive at that C. So on one side, it would be a negative slope. On the other side, it would be a positive slope. Now, doesn't it kind of make sense if my slope is negative and then it either goes 0, then it goes 0 and then back to positive? What does it look like the graph is doing? The very bottom is bottoming out, so it would have a relative min there. But that works not only when the slope is 0, but what if it was like a cusp, right? Negative slopes all the way through here because it's decreasing. Positive slopes through here because it's increasing. No derivative there, so it's undefined at the cusp. What did that form though? Relative what? Min. So if it's a critical number, which could be a slope of 0 or d/e, changes from negative to positive. So if the derivative goes from negative to positive slopes, then the function has a relative min there. All right? So what about this? What if the derivative changes from positive to negative at that C value? Positive slope, 0, negative slope. What's that look like? Relative max. Might be a max. I'd have to check it along with all the other endpoints, right? And all the other critical numbers. But right here, I know it would be relative max, even if it was increasing this way to a cusp and decreasing. So whether the derivative exists or not there, if it increases, decreases, there's got to be a point there, and there's either derivative is 0 or d/e, that's going to be a relative max. And then right here, if the derivative does not change signs, but stays like negative slope, 0, more negative slope. Well, I call that a layout or a horizontal tangent for one instant, but it's certainly not a max or min, is it? Or if it goes positive slope to 0 to positive slope. Well, that wasn't a relative max either, was it? And if you go back to pre-calc, it's not a relative max, even though on the right side it looked relative, on the left side it didn't. Okay? So if it lays out like that, or, and I didn't put this on here, it could also positive slope, d/e, more positive slope, right? So the slope could either be like a d/e or a 0 slope. You with me? And neither one is going to be a relative max or relative min. But if it's a critical number and these two things happen, either negative positive or positive negative, I know there's a relative something there. You with me? And shockingly, that is a massive topic in APCalc. And most people go, sweet, I love that topic. Okay? Now, it's going to maybe look a little different from time to time, and you're going to have to figure out if it's negative or positive. You might have to do some checks, but we're going to do that a ton. Okay? So even if I can't see a picture of the graph, I could check values on either side, kind of like we do with limits sometimes. And if I check, like for instance, if I check a derivative, and I get 0, I go, oh, well, let me just pick a number a little bit to the left of C, and usually it doesn't even have to be, like, it could be just 1 to the left, right? Or 1 to the right. We'll talk about that. You don't even have to pick, like, Like if C was 5, you don't have to pick 4.9 and 5.1. You can just say 4 and 6. And you just check on either side, and if one side's negative, the other side's positive, you go, oh, must have been negative, 0, positive, must be a relative min. So we're going to do all of that, but these rules are very important, and this is called the first derivative test. All right, and remember, there's another second derivative, much less used, not quite as helpful, because you actually have to take the second derivative to make sense of it, which is more work. But you can actually do something with the second derivative to determine relative maxes and mins too. We'll get to that in a bit. Are we with me so far?
Yes.
Okay, so let's take a look. So what if I gave you, it says find the intervals where this would be increasing or decreasing. So we're starting slow. I'm not asking you where maxes or mins occur yet. I just want to know where this function increases and decreases. Now think about it. We're about to use calculus to determine when this thing goes up or when it goes down. That's actually kind of a big deal. We can actually start sketching a pretty decent looking graph without our calculator, just using our calculus. So here's what I'm going to do. I know that it increases when the derivative is what? Positive. It decreases when it's negative, right? When do you think it changes? And when the derivative is 0. So why don't we just find these critical numbers? So I'm going to take the derivative of this thing, I'm going to set it equal to 0 or d and e, and the only reason I didn't mention d and e here is because, why? It's a polynomial and it is not going to have a denominator or a square root. So here's my derivative. 3x squared minus 3x, set it equal to 0. And make sure that you see the derivative and the equal 0 in there somewhere. Factor it. And man, look, the factoring is so much easier than algebra 2. Algebra 2, we try to intentionally harm you. With factoring, no more. Basic GCF, basic trinomial stuff. I'm not saying you're not going to have issues, but if you have issues, I still remember this guy named Riley in the back. I was like, guys, you got to learn how to factor. He was like, I can't factor. And he was like a 3-time math team or whatever, but he said he built up some Pavlovian reaction, fearful reaction to factoring back in like the Tyree era, and he never recovered from it. And I was like, just come see me. So he came back and I went over some factoring. He's like, that's it? I'm like, yeah, dude, you don't have to remember all that junk from Algebra 2 where they just pummeled you with it. He goes, oh, all right, I like factoring. So if you're one of those, remember, first step to recovery is admitting you have a problem, and come in here and I'll help you and you'll be fine. But it will kill you not factoring correctly on this test. Because if you don't factor well, then you don't get the right critical numbers. If you don't get the right critical numbers, your graph becomes a disaster. And you'll see that in a second. So, can you see right here my critical numbers are 0 to 1? And notice I'm not even dealing with an interval here. So I'm not asking you about maxes or mins. I'm just looking at relative maxes or mins. In fact, you should know right now that this doesn't have a max or min. Somebody tell me why. Because it's a cubic graph. It goes up forever, down to forever. And if there are no intervals, I know it's going to infinity, negative infinity. Therefore, there is no one y value bigger than all the others or smaller than relatives. Right? But I bet there's some relatives if there's like a little wiggle in there. And I'm betting they occur right here, if there are any. Because according to Fermat's theorem, if you're going to have a relative max, it's going to occur at critical numbers. So let's take that 0 and 1, and I'm going to mark them on a number line. Now, in the olden days, they would allow you to use what they call a number line analysis, and you could just fill it in and they would go, oh, yes, I know exactly what you're talking about. Because so many teachers do these differently throughout the country, they don't accept number line analysis anymore. Now, we're going to do them because it's a great way of thinking. But literally, the AP reader is told to cover it up and not look at it. So what we're going to do is the best way to think through this problem is the number line analysis. I'll show you how to do this. But then we're going to look at it and we're going to write out what we see from it. And that's what gets graded. Okay? So here we go. Say I have this function. I'm just going to mark the x-axis. You don't really need to mark an y-axis. And I found that the two critical numbers were 0 and 1. So I'm going to mark 0 and 1. All right? Then I am going to say f and f prime. So what I'm going to do is I'm going to learn about what f prime is saying, and then I'm going to do a little mock sketch about what that would look like with no y values, but just increasing, decreasing behavior. So what do I know is happening at 0 and 1 again on the f function?
Changing directions.
It's flat. And I know it's flat because the derivatives were 0 there. Those are critical numbers, right? So I know it's flat, but I don't know if it's up, flat, down, like I do by looking at this, but or down, flat, up, or maybe up, flat, more up. I don't know that yet, do I? I mean, you do because I've done the work, but if you didn't have this finished. So I am going to check the derivative to the left of 0. So I'm going to plug -1 into my derivative to see what the slopes are there. And when I plug -1 into the derivative, what does it give me? -1 in the derivative. I get a negative times a negative, which is a positive. Or if I plug it into the factored part, but check it out. I plug it into this because it's easier for me to go negative times negative is positive. It doesn't matter how positive it is, right? So I usually do that. And then I go, oh, since it's positive, based on my rule for increasing, when the derivative is positive, what does the function do? Increases. So I just draw a little line for increasing. You don't have to put increasing if you want. Right? And then I check in between 0 and 1. So maybe I take a half out. And again, it's easier for me to plug a half into this and see if it's positive or negative than into that. I really don't want to go, oh, 3 times a fourth minus 3 times a half. Forget that. I plug a half in here and I go positive, a half in there, negative, plus times a minus gives me a negative. So I know that from 0 to 1, this interval is negative. And what does it mean about the function when the derivative is negative? It's decreasing. And then I plug 2 into that same thing, and what do I see? Positive times positive, which is positive. So if the derivative is positive, the function is increasing. And now I look at this, and the first derivative test comes into play. What does the first derivative test tell you about when the function goes from increasing to decreasing, or when the derivative goes from positive to negative? It could be, but what does it tell you? If it's a critical number, which it is, check it out. First derivative test. If it's a critical number, which it was, if the derivative changes from plus to minus at C, if the derivative changes from plus to minus at the critical number, what is it? Relative max. And it just looks like one, right? Relative max. If the derivative changes from negative to positive at a critical number, what is it? Relative min. Now, does that mean that the relative max is 0? No. It just means the relative max is at 0. To find the actual max or min, if you had to find it, that's a y value. So where would you plug that? In the original function or the derivative? In the original, because I want to know the y value there. So if I plug that back in the original function, what do I get? 0. So the max, the relative max is actually at 0. And what happens if I plug 1 back in the original function? Negative a half? I'm not looking at the function. So the min would be at negative 1/2. The relative min would be at negative 1/2. Now, here's what I have to write for the AP reader. Okay, so what is this telling me? And the question was, where is the function increasing or decreasing? So the function is increasing from negative infinity to 0, notice no brackets, and from 1 to infinity, notice no brackets. It's decreasing from 0 to 1. And I would probably not write that much. I would say f increasing negative infinity to 0, 1 to infinity, and you can put a comma also. And then I would say and decreasing 0 to 1. And I'm going to make it as simple as possible and move on to the next question. But if you got some free time, you want to write all that and knock yourself out. Tracking with me? Look, I got a pretty good idea what this graph looks like. And if I find those mins, which I didn't need to on this problem, if I found him, I could be like, oh yeah, at 0, I came up like this and had a peak right there at 0 at the origin. And then I dipped down a little bit, and at 1, I was down there at negative 1/2, and then I started cruising back up again. And we're going to learn more than just about increasing and decreasing to even do a better graph. And I know in the whole scheme of things, you're like, ooh, boy, I could do a graph. Why did I spend $150 on my calculator? I get that. But we are going to show some better, like some real world applications, but we got to learn how to crawl before we can actually run. Okay? Questions. Why does it matter which value I check with the derivative? Why doesn't it matter? Why doesn't it matter which value I check with the derivative? That doesn't even make sense to me.
Doesn't matter which value is one, which value. Negative more.
Is that what I'm trying to say? I need to word that better.
Negative seven.
Okay, yeah, so why am I picking, why does it matter? Because everything in this interval, right, is gonna be negative, so it doesn't really matter. Maybe that's, I need to word that better. Is it possible in the situation above that between 0 and 1 the graph decreases and increases in that same interval?
Because there would be another critical.
Because there would have to be another critical number, right? And there aren't any other critical numbers. And then, we just answered that, why we're not. All right, so let's look at this. This one now jumps to actually finding the relative extremes. So we're going a little bit further, and notice I'm giving you a fractional exponent, which is probably going to throw something in the denominator, isn't it? Okay, so let's take a look. It says, this is a similar question, blah, blah, blah. We'll just move on. So we're looking for the relative extremes. So what would you do first? Find the derivative. Do I give a, nope. So, to make enough room here. X squared minus 4 to the 2/3. Okay, so here's my function. So if I'm taking the derivative of it, what would you do? 2/3. All that jump, because I really don't have a trick for this, to the negative 1/3 times 2x. Now I'm going to write that better because that bothers me right here, which is why I taught you that form on the square root, because that shows up a lot, gets you really in a nice form. But right here, I'm going to clean this up. So what stays in the numerator here? That 2 and that 2x. I'm going to leave 4x there. What ends up in the denominator? This 3, and then what does the 1/3 mean? Cube root. What's the negative mean? On the bottom. So I end up with the cube root of this on the bottom. So there's my derivative, and I need to show two things, where it's 0 and where it's DNE. So the first thing is, if I just tack a 0 on it, where is a fraction 0? When the numerator is 0. So I know that the numerator is going to be 0. 4x equals 0 when x is 0. Right? Now, you also need to check, where is the derivative not exist? When is that true? The denominator is 0. Now, it's okay to write the whole denominator, but what ends up really making this 0? Which part of it? Even more specific, the inside of that square root would have to end up being 0, right? So if you want to divide by 3, you can, and then cube both sides, you can, but guess what you end up with? Well, no, you end up with just this. So really, the only thing that can make this 0 is if that's 0. So if you want to jump to that, you can, and then this factors and leaves you what? Plus or minus 2. Do I have an interval to be concerned about? No. Do I have to worry about anything about negatives under the radical? No, because it's a cube root, right? So I've got 3 critical numbers. So I would come down, I would mark these on my number line, and I am going to do what? Put f on the top, because I'm going to sketch what the actual function would look like, but I'm going to be checking f prime on the bottom, because that's what I'm going to learn about the derivative's behavior there. And again, what do I know about negative 2, 0, and 2? Think about it for a second. At 0, what's happening? At 0, the slope is 0. But at negative 2 and 2, the slope is DNE. So remember that when you're graphing it. Don't make at 2 and negative 2 the graph be flat there, because the derivative wasn't 0 there, right? The derivative is flat here, but it's probably like a cusp or a going vertical here. Now, could it be a vertical asymptote there? Because the derivative doesn't exist.
Yes.
At first glance, I think yes. I'm glad you said it, because I want to leave. But does this have vertical asymptotes? No. So since that was defined everywhere, I'm guessing it's a going vertical or a cusp. Is that making sense? Okay, because this didn't have a denominator originally. So let's take a look. Let's see. What if I check the derivative at say, and pick good values. If you, I mean, don't pick something you don't want to pick. You can pick any number to the left of -2. I'm going to throw in -3 just to see, but plugging that in here, what do I end up getting? On the bottom, I get 9 minus 4, so all that's positive. And again, I don't need the value, I just need whether it's positive or negative, right? And then on the top, a -3 gives me negative. Negatives over positives are negatives. So since that was negative, must be decreasing there. Right? Does that make sense? Okay, -2 to 0. I'm going to check the derivative at -1. All right, so at -1, what do I get on the bottom? -1 squared is 1. 1 minus 4 is negative. Cube root of a negative is still a negative, not an I. That's only with square roots. So the whole bottom's negative, and if I plug a negative on the top's negative, right? So negative over negative, positive. So if the derivative is positive, what does that tell me? It increases. Now, a lot of people make the mistake of going, oh, this curve must be doing this here. But wait, the derivative doesn't exist there. So instead of doing this, what's it probably doing? Probably doing that. Because it's not defined there, the derivative at that point. Does that make sense? But you would have to be able to discern that if you were sketching this curve. 1040, okay, we got it. And then between 0 and 2, if I check the derivative at 1, positive on the top, negative on the bottom, decreasing. And if I check the derivative at, say, 3, positive on the top, positive on the bottom, increasing. So, at first glance, it looks like it might be going down, up, down, up. But if you really think about it, because right here, the derivative didn't exist, I'm guessing this curve does that, right? Right here, because the derivative does not exist. Now, we don't need to know that on this curve problem, but that's where we're heading. I'm guessing the curve does that, right? But here, what happened? The derivative was 0, so I'm guessing that it actually flattened out up there. So this curve actually looks like, does that. But it increases forever. So it's not going to end up going down. How do you know that? It's doing that forever. So this thing probably does this, just heads up, flattens out somewhere, and then just keeps heading up. And that's probably what this graph would look like, but we're going to learn even more before we graph it. Now the question was, what? Find the relative extremes. So what would you do to find the relative extremes? You know that there is a decreasing, increasing critical number. That's a relative min there. Relative max there, relative in there, but what do you have to do to find them? Plug in the -2 and 0, -2, 0, and 2 into the original function. So we'll just say, all right, if I plug -2, and this may be a mess, don't worry about simplifying it. If I plug -2, I'm going to erase this, into there, what do I get? 4 minus 4 is 0, 0. So I have a relative min of 0, and if I plug a 0 in there, what do I get? -4 to the 2/3. Okay. Relative max at -4 to the 2/3 power. And guess what -4 to the 2/3 power gives me? That's the same thing as what? The cube root of, so cube root of 16, right? Ends up being positive. That's my relative max, right? And then I got another relative min where? Another relative min of +2 in there also gives me 0. So I have mins of 0, max of cube root of 16. And if you're looking at that and going, ugh, am I going to get weird answers like that? Probably not on the AP test. Possibly on mine, but guess what? AP lets you leave it like this. Now I know people who leave it like that, they go, how can I have a max smaller than my min on either side? That kind of is weird. How would that happen? Well, that was your confusion because you didn't see that ended up being positive when you squared it. And I can keep doing these. That was example 2. I think I had another 3 for you. The bell's about to ring, so I'm not going to be able to talk anything about this, but do what you can on the homework, guys. Bring in good questions. Email them if you have issues. Try to do it. I'm actually going to leave early today at 4:45. Be my first time home before 7 in 2 weeks.
We have assignment sheets.
Am I not giving you one?
No.
Not bad. Yes, I do. Oh, and there's a really good chance that I'm gonna be bailing on this whole, like, have y'all been functioning well from this?
Yes.
Oh, yeah. I mean, I like the ones last year better, but like,
What do you mean? This is the same as last year.
like in really small exams.
Oh, no, I mean, can y'all function with this well as opposed to the Schoology?
Oh, yes, this is so much
Yes.
better.
That's what I'm hearing from everybody. Like, I think this is I've gone forward through this period, but after this, I think what I'm gonna do is instead of going week by week, I don't even care what they're telling me anymore. At some point, I probably shouldn't put that on video, but I'm gonna start putting section by section. So I'm gonna be like curve sketching, and you're gonna go in there, and it'll still be chronological for you, day by day, but I think we're all, as soon as we get back together, and everybody's here, I'm not gonna go week to week, I'm just gonna go day by day, and you'll just look in the thing, and you'll see it all chronological. And it will mirror this, and that will save me 8 hours a week. All right? All right, guys, good talk.
Good talk.